Hello ECA students, welcome to another week of online learning. This week we are starting a new unit of nuclear chemistry. Here's the drill. You're used to it. We're going to have a quiz, a reading response, and a lab activity, and this week is worth 50 points. Here is what this slideshow is about to cover. To save time, I'm going to skip through it, but you're welcome to pause it and copy for notes. All right, alchemy. The ancient alchemists dreamed of changing one element into another, such as lead into gold. However, they were never actually successful. You have worked with chemical reactions, but chemical reactions just involve the electrons of atoms. The nucleus of the atom doesn't change, and its identity stays the same. In nuclear chemistry, we look at the nuclear reactions that do in fact have the ability to change the identity of an atom. Ancient alchemists' dream of changing one element into another has come true, and it's called nuclear chemistry. So to review, first semester we looked at the atomic model. We learned about isotopes already, but let's review them just for this unit. The number of protons we know determines the element, but the number of neutrons can vary, and these variations are called isotopes. Due to nuclear stability, some isotopes are more common than others, such as carbon-12 is more common than carbon-13, and that's more common than carbon-14. Tongue twister there. The atomic mass is the average atomic mass of all the isotopes added together. So modern atomic theory has us looking at forces again. We looked at intermolecular forces before, but today we're looking at forces within the nucleus of an atom. Protons and neutrons are held together by a nuclear force, a strong attraction that is only functional at short distances of 10 to the negative 15th meters or less. At greater distances than 10 to the negative 15th meters, the nuclear force is very weak, but the electromagnetic force of repulsion of like charges, positive, negative, electron, proton, is stronger. Like charged protons experience a repulsive electromagnetic force when they are too far apart, but when they are close enough together, they are attracted to each other through the nuclear force. Again, depending on the isotope, some nuclei have more stability than others. So what we know so far? We know that some nuclei have more stability than others due to the isotope, and we know that some isotopes are more common than others. We also know that in nuclear chemistry, we can change the identity of an atom through nuclear reactions. So let's use this information to tell us about radioactive decay. An unstable nucleus, we know, wants to be stable. So how does it do that? In order to become a more stable nucleus, it must emit subatomic particles, which can change the isotope or even the element itself. It also releases lots of energy to become more stable. Let's talk about the three specific types of radiation: alpha, beta, and gamma. An alpha emission is the expulsion of an alpha particle from an unstable disintegrating nucleus. This particle is simply a helium nucleus. Once emitted, it can be stopped by a piece of paper. It can become a complete helium atom by acquiring 2 electrons. A beta emission is the expulsion of a beta particle from an unstable disintegrating nucleus again. A beta particle is simply an electron. Beta particles won't be stopped by a piece of paper, but can be stopped by a thin layer of metal, such as a 1 centimeter thick piece of aluminum. The electron can remain free or become part of an atom. Last but not least, gamma rays. A gamma emission is a high energy burst of electromagnetic radiation from an excited nucleus. It's an electromagnetic wave that is so energetic and the wavelength is so short that it can't be detected by the human eye, such as regular light. It It is the most penetrating type of radiation and can pass completely through a person, but it can be stopped by a 5-centimeter thick piece of lead or a really thick concrete wall. Gamma radiation is absorbed, and it gives its energy to materials that absorb it, such as heating them up or causing chemical reactions within them to occur. During radioactive decay, the parent isotope can decay into a daughter isotope, and potentially alpha, beta, and gamma radiation. In nuclear reactions, atomic particles are smashed together to create a chain reaction, and energy is released. Through these reactions, atomic nuclei can form new elements by splitting or joining. Splitting and joining are called nuclear fission and nuclear fusion, respectively. Nuclear fission is when heavy nuclei split. Sorry, there's an error there, not nucleus. Nuclei is plural for nucleus. Heavy nuclei splits or fissions. And nuclear fusion is where atomic nuclei of low atomic number fuse. They are very easy to get confused, so watch out on your quiz. But both these nuclear reactions release incredible amounts of energy. See? All right, fission. Fission occurs when a neutron hits the nucleus of uranium atom, causing it to split in two, or fission. More neutrons are released, and these hit more nuclei, creating a chain reaction. So, fission occurs when a single neutron hits a nucleus. That neutron causes the uranium nucleus to split. The nucleus goes through radioactive decay, and the atoms split apart, releasing energy, emitting more neutrons. The neutrons carry on the chain reaction to nearby uranium atoms. Nuclear fusion. Nuclear fusion occurs when two small, meaning low atomic mass, atomic nuclei join. Two isotopes of hydrogen can be smashed into each other to make helium, while at the same time releasing energy and a spare neutron. Fusion takes place in the stars, but advances in harnessing fusion energy on Earth have not been achieved due to the immense heat and pressure needed to start the process. But we will revisit this topic later on in this unit. All right. The fusion process occurs by hydrogen isotopes, deuterium and tritium being smashed together and fusing. Deuterium has 1 neutron and tritium has 2. Typical hydrogen is just a proton and an electron called protium. The product of the fusion reaction is helium, which is an alpha particle, a neutron, and energy, such as gamma rays. Fuse. They fuse together. All right. So, something interesting. In nuclear reactions, there's a loss of mass. Where does that mass go? That doesn't follow the law of conservation that we've learned about, which states that matter or energy is neither created nor destroyed within a system. So, we can explain this phenomenon using Einstein's famous equation E equals mc squared. The change in mass is actually related to the energy change. E stands for energy, m stands for mass, and c is the constant equal to the speed of light, or 3 times 10 to the 8th power mass meters per second. According to this relationship, matter and energy are essentially the same thing, and one can be changed into the other. The difference between the mass of an individual neutron and the mass of a nucleus is called the mass defect. In other words, if we count up the individual mass of neutrons and protons, they would have more mass when they are together than they would have more mass separated when we add that mass than when they are together in a nucleus. The mass defect is the missing mass. Where did this mass go? Again, we use Einstein's equation. When the nucleon joins to make a nucleus, energy is released and the more stable nucleus is formed. The energy is called the binding energy and is equal to the energy needed to split a nucleus into free neutrons. The binding energy of a nucleus of any isotope can be calculated by the mass defect of a nucleus. So let's look at that. Some nuclei are unstable because they are too large or have an unstable proton to neutron ratio. And they undergo radioactive decay until they reach a state of stability. The ratio of binding energy per nucleon stands for protons or neutrons, reflects the stability of a nucleus. If you graph this ratio over atomic mass, an interesting pattern occurs. We notice that lighter atomic nuclei will have rapidly increasing binding energy as atomic mass goes up. But once we reach a peak of atomic mass 56, the binding energy goes down. Iron 56 has the greatest binding energy per nucleon and is the most stable nuclei out of any other atom. Lighter nuclei that have unstable proton to neutron ratio will go through fusion if in the right environment, say a star, and unstable nuclei that are too large will go through fission. All right. That wraps up this slideshow. Thank you for watching and good luck with your assignments this week. If you have any questions, please email me. Thank you.